All right, so really what I'm trying to show you here is how we predict what the shapes of molecules are. And you can do this with any kind of standard like round object. I just have a ton of these sitting around right now because I got them from my cousin. But anyways, these are apricots. Um, let's say you had two atoms, right? And they're bonded together like that. And we could use for bonds, we can use toothpicks, like I can jam a toothpick. Uh, but it's messy. I'll have to do that here in a little bit. But that would be linear. Anytime you have two, right, 2 points sort of define a line, we call that linear, right? So now what happens is this. If I place a cherry in the middle, I got those from my friend's place too. So you notice this shape, right? This is actually would be the shape of molecule. Now, the cherry doesn't have to be smaller, right? The central atom doesn't have to be smaller for this to happen. But the way I've done this is I've put them across from each other. So this is also linear. And the reason it's linear is you have to remember these atoms on the outside, they're going to have what do you call it? A negative charge on the outside. And because of that, these two atoms, remember these apricots are atoms, these two atoms will want to get as far apart from each other as possible. So that's what gives us this linear arrangement. Now the question is, what happens when this third one comes in, right? Like if I do that, and you look at it from the top, you can see like this is not well balanced. That is, these two groups could be further apart from each other. So what ends up happening is this. So you can see the way I've got this, these are at the corners of a triangle. Like I can draw a triangle on top of that, and that would be the corners of a triangle. This is known as trigonal planar because if I go down to the side like this, you can see that all of them are in the same plane. And this is how you get maximum distance between three atoms or three groups around a central atom. Now, it makes a lot of sense right now because I'm talking about this in terms of atoms, and you can definitely see these. But it turns out lone pair electrons, like we have on a central atom. So, for example, if I have a nitrogen with a lone pair, those occupy the same kind of space that an atom does just because of their negative charge. So you don't see them in terms of like them being atoms there, but they do have that effect. So if one of these was a lone pair, it would still be trigonal planar in terms of the arrangement, but we'll have a name for that shape because it'll look different. It'll actually look, oops, like that to us. I didn't mean for it to fall apart like that, but it'll look like that to us, and it'll still be bent, right? Because there'll be a pair of electrons sticking out right here that pushes these two groups away. And in fact, that's the name of this shape. It's just called bent. Now, what happens if you have four? So it turns out 4 is like the easiest one to do because it's just like that. Now, this cherry is like smashed inside of there. But this arrangement that you're seeing here, this shape is known as a tetrahedron. It's just like 4 fruits stacked together, but in the inside, there's an atom sitting there between all 4 atoms. And that would be our central atom. And so we're going to actually look at structures that would take on this tetrahedral shape. So really, if you want to build this at home and just to have it as a reference, right, all you really need to do is have a bunch of fruit sitting around. And that's pretty easy to do around here. All right. So this theory, we call it VSEPR theory. VSEPR. It stands for valence shell. Because remember, we're talking about valence electrons when we make these bonds. Valence shell, electron pair, repulsion. So again, a central atom will have electrons around it, electron groups like other atoms, right? And these groups, pairs, because they're bonded together, will repel each other. And the goal of VSEPR theory is to try to find the arrangement which maximizes the distance between the atoms that are on the outside of the molecule, okay? So when we say shape, it says we're referring to the shape around the central atom. So electrons repel each other, and what we can count as electron groups include all of these things. A single bond is one group. These all count as one group. Like a lot of people miss that this says one here, but each one of these, even though it's a triple bond and it's three pairs of electrons, right, they're all pointed towards another atom. And so that means, right, it acts as one group of charges rather than three separate groups as three lone pairs would be, for example. So we're going to have something called the electron geometry, okay? That's actually what I was showing you for the most part with the fruit. Those are called electron geometries. We would think about that as the way the atoms and lone pairs are spaced out. And then there's the molecular geometry, and molecular geometry is really what we think of as shape. Right? This is the shape of the molecule. Not how the electron pairs are arranged, but how the atoms are arranged rather than just electron pairs. So this is how atoms are arranged. So I'll say atoms arrangement. All right. So as I showed, if you have two electron groups on a central atom, the electron geometry is linear. It has zero lone pairs, and the molecular geometry is also linear in this case, okay? The bond angle, when it's linear, is 180 degrees. So that's like, oh, I ate the cherries. I was going to say, it's like when they're like this. Here's their central atom is now an apricot, right? That angle between this apricot and this apricot, that is 180 degrees, okay? That's what we're talking about. All right. Now, you could have three electron groups, and this is the electron geometry that we call trigonal planar. That was the three apricots surrounding one cherry. I didn't have any lone pairs in that one. And whenever the electron geometry has zero lone pairs, the molecular geometry has the same name. So this would also be trigonal planar. Now, if you have three atoms like this on a central atom like this, right? Let me blow this up so we can see it a little clearer. And you think about bonds like this angle, that's 120 degrees, like that. And then, remember, when I took one off, right, I had the electron geometry still trigonal planar. Remember when I took the one apricot off and just said there was a lone pair there, so I had one lone pair? We just call that bent. And this is often like TP, right? So this would be TP, and then it would be bent. Because it turns out you can get bent geometries from other electron arrangements, and I'll show you that in just a second. So it's bent. The bond angle is actually less than 120 degrees. And the reason it's a little bit less than 120 degrees, it turns out lone pairs take up more space than atoms do. You wouldn't think, because of the way I did it and I made these things so big, right? But lone pairs actually will occupy more space. And so what that does is if you have a central atom in the middle, it bends them away from each other, okay? So it's going to be less than 120. That's when you have a situation like this, and there's a lone pair. This will be, oh, it looks like he's frowning. All right, this angle is less than 120. Now he's smiling. Like that, okay? So when we talk about bond angles, it's the angle between the atoms and not between the lone pair of the atoms. Now we get to the 4. If you have 4, right, and no lone pairs, this is what we call tetrahedral. If you're describing it, the actual object is called a tetrahedron, like adjective versus noun kind of thing. But tetrahedral geometry. And if you have no lone pairs, it's also tetrahedral. That bond angle, it turns out, it's not a hard like mathematical proof, but it takes a long time. Most people don't care, so it turns out it's 109 degrees, 109.5 actually. And then let's see. yeah, what if you have one lone pair, right? So what that means is it's going to look something like this. And that would be this shape that I'm showing you here, right? So you'll have three atoms at the bottom, right? Like here. And then a central atom like this. It's elevated above the rest. And this is actually, and there'd be a lone pair up here, like where this toothpick, I'll just jab it with a toothpick really quick. Like that. That's where a lone pair would be. So, you know, if it's tetrahedral, then that's replaced by an atom. So that would be like that. But if it's trigonal, a trigonal pyramid, right? You can draw a pyramid out of the spheres here. It has a lone pair at the top, right? That's what we call a trigonal pyramid, and because this is a lone pair and actually occupies more space than one of these atoms does, it makes this bond angle, the angle between these atoms, makes it smaller. It actually squishes them together, okay? Which I didn't really want to squish fruit here, but anyways. So that means we have tetrahedral here. So the electron geometry doesn't change, but the shape now becomes a trigonal or trigonal pyramidal. So you have a central atom, and then you have like three things coming out, and this is what makes it. And this is a dashed line. It's not very good artwork, but that's what we mean by a trigonal pyramid. You have atoms at the bottom like this. Those are those apricots, and then the cherry that's binding them all together in the middle. Now there's a lone pair over here, but we don't count that as part of the shape of the molecule. We just count the atoms as part of the shape of the molecule. That bond angle is actually less than 109.5. Okay. Because this lone pair, like I said, exerts enough pressure on these atoms down here that it literally squeezes them together. And if it had been apricots, I could have squished them together and made a little juice come out perhaps, but that was just a little messier than I wanted. And then the last one is when you have a tetrahedral, and it has two lone pairs, and then we just call that tetrahedral bent. So anytime you think about, like, if you take this structure that I just drew and then you just redraw it, it would look like perhaps drawn like this, but then it would have two lone pairs like this coming off on the sides. This angle is less than 109.5 as well. And it's probably much less than 109.5 in comparison to a trigonal pyramid. But again, we have two different bent shapes. So anytime you have two atoms to a central atom, we just generally call that bent. But then you have to designate whether it's a trigonal pyramid or trigonal planar, or a tetrahedron. Okay. So let's do some examples. And I'll get back to this wedge and the hatch thing. Let's do some examples for CO2, right? So these Lewis structures are drawn and they're complete. And so what I'm just showing you how to do is predict what the shape is. But you have a central atom, right? And you have two atoms around the central atom and no lone pairs. When I say no lone pairs, I mean there's no lone pairs on the central atom. If there's lone pairs on the central atom, it causes the oxygens to move away from each other, but since there are none, the oxygens can be on opposite ends, and that becomes linear, okay? Now, if you look back at this table, it's two groups, with no lone pairs on the central atom. That's the key part, right? And we'll go back to our table, right? Two electron groups here and zero lone pairs. It's linear, and that bond angle will be a 180-degree bond angle. Now, let's look at SO3. That's not SO3 2 minus. That's just SO3. When we look at SO3, I have how many groups on the central atom? Again, it doesn't matter if it's a double bond, single bond, triple bond. Those are all counted as one group, right? So this is one group here. This is one group here. And this is one group here. So now I have three groups and no lone pairs. And again, there are lots of lone pairs on this structure. There's just none on the central atom. And so think about that. If you have three groups, that's this, right? They can all be spaced apart from each other like that. And this is flat, right? So this is trigonal planar. And the bond angles are 120 degrees. Now, let's go to scroll back up. Three groups, no lone pairs, right? So I have three electron groups, 0 lone pairs. So that's where I would look if I had the table. And of course, you're taking this task basically as a take-home. Have the table, draw the structure and have the table in front of you, right? And then use that to get the shapes and the angles. Let's take a look at, let's do this one, NH3, right? This is a group, this is a group, this is a group, and this is a lone pair on the central atom. And so this becomes 4 groups, 1 lone pair on the central atom. Right, and again, this takes you back. 4 groups would be tetrahedral. 1 lone pair would be trigonal pyramidal. That's the shape. So it's still tetrahedral electron geometry, but the shape of the molecule, the molecular geometry, is trigonal pyramidal. Or it's a trigonal pyramid if you want to stick with the noun. So this is what I want you to do. Take these next two, the H2S and the CF4, and determine what the electron and molecular geometries are. I'll pause it here and I'll pick up with the H2S. Okay, so 4 groups, 2 lone pairs, right? This is bent. So that's what you should have come up with. And the bond angle is less, I didn't ask you this, but the bond angle is less than 109.5. Oh, I forgot to say tetrahedral is its electron geometry. I get that from here, and I get the bent from the 2 lone pairs. So go ahead and do this one. I'll pause it again, and I'll restart. Okay, so there are 4 groups. Each one of the fluorines counts as one group. There's 0 lone pairs. There's lots of lone pairs, like I said, on the structure. None of them on the central atom. So this becomes tetrahedral for both, because there's no lone pairs. It's tetrahedral for, I left a bunch of words out. Tetrahedral for both the molecular and electron geometries. And the bond angle will be right on 109.5.